Welcome back. So I know we've had a little bit of time to talk about three-dimensional problems and a little bit of time to talk about angular momentum. But today I want to be a little bit formal, well, as formal as I ever am, about driving what it means to have a wave function in three-dimensional space under certain symmetrical conditions. Okay, so let me remind us of the process that we've been using so many times when we're trying to come up with learning about bound states of different types of potentials. Okay, basically, what I want to do in many parts of quantum mechanics is I want to solve the eigenvalue problem for the Hamiltonian. That is, I want to find out if h psi equals e psi has solutions for which the energy is quantized, or in some cases for which the energy isn't quantized, right? I want to find those states that have a definite energy. There's lots of good reasons for doing that, but it always comes down to this process of trying to find those states. In order to solve the eigenvalue problem, I have to, well, first choose a basis, right? So in the old days, the basis that we used was, the spin basis, right? And we decomposed it onto eigenstates of the spin Hamiltonian. Then we worked up to one-dimensional potentials, right, where the basis that we chose to work in was the position basis, right? And then I could write down this equation in the position basis, and I got a nice second-order differential equation. And then solving that second-order differential equation meant first finding the general solutions. For example, in the case where the potential was constant, right, it was either e to the ikx or e to the kx. And sometimes I had fancier things, right, with, say, the harmonic oscillator. But after I found the solutions, the general solutions to those problems, I would impose the boundary conditions in that space to give me what the quantization conditions were. And that would tell me both what are the states and what are the energies, right? That's the process. Start with the eigenvalue equation, put it in some basis, solve the equation for the general solution, and then impose the boundary conditions. And so what does this mean in 3D? Well, I have to choose a basis, right? We're still going to use a position basis, but now it's a three-dimensional position basis. I have to write down what the Hamiltonian looks like in that basis, right? So in 3 dimensions, my momentum is a vector, right? So when I talk about the momentum squared, I'm really talking about the momentum operator dotted with itself, which gives me that scalar minus h bar squared times the Laplacian, right? And therefore, the full Hamiltonian in the position space representation is going to be something like minus h bar squared over 2m. You're already tired of writing that down. That's sort of the rite of passage for quantum mechanics classes, that you write that down so much that you start crossing your h's even when you're not doing quantum mechanics. But minus h bar squared over 2m times the Laplacian of the wave function plus the potential times the wave function is equal to the energy times the wave function, right? This is still an eigenvalue problem because I don't know what those energies are and I don't know what the states are yet. But it starts to look like a differential equation. Now, it's a partial differential equation, right? Because my wave function is going to be a function of x, y, z, or r, theta, and phi, right? It's always going to be a function of 3 different things. In fact, the whole class of potentials that we're going to be studying this week are going to be those scenarios in which the natural coordinates to use are actually going to be the spherical polar coordinates, because I'm going to assume that my potential is just a function of r, right? So I'm imposing spherical symmetry on the problem, and by imposing the spherical symmetry on the problem, my potential then only belongs to the r direction, but at the cost of having to write down the Laplacian operator in spherical polar coordinates. And this is not our favorite way to write down the Laplacian operator, right? The Cartesian coordinate system is the one where the Laplacian operator really makes us happy. But I digress. We're going to have to live with what we got here, because for so many problems in quantum mechanics, for example, the hydrogen atom, right, we're going to get to a point where the potential only depends on your distance from the center. And if your potential only depends on the distance from the center, then we're going to have to use spherical polar coordinates. Okay, and that's expressed with r, theta, which, to remind us, is the angle down from the z-axis, and phi, which is the azimuthal angle which goes around the z-axis. So when I plug that into this equation, the eigenvalue equation, I end up with a big mess. Right? I guess it's not so bad, right? If you took E and M, this is something that you became a little bit more comfortable with because you saw this Laplacian so many different times. But I have a Laplacian that has these 3 different terms which have partial derivatives with respect to each of my coordinates, and then I have my potential term, and I have, of course, on the right-hand side, the energy, which is the eigenvalue, which really, at the end of the day, is the thing that I'm really desperate to get, right? I really want to get those energies. So that's step one, right? I've written down the eigenvalue problem in some basis. My next step is to solve this equation, right? So now I have to come up with some method of solving the equation. Now, people have done this for us, right? Or equations of this style. So if you've seen this in E&M, or if you've taken a different quantum mechanics class, the method that we're going to use to solve this problem is one that's known as separation of variables. Now, would you have known this if you had walked into this class off the street and never had taken an E&M class? No, right? But that's in the textbook. That's why it's in the video, right? This is the method that we're going to use to solve this kind of problem. It's frequently used for solving Laplacians, but it basically goes like this. I'm going to make a guess, an ansatz, that my wave function can be written as the product of two different functions, which for the time being I'm going to call r, which is a function of r, and y, which is a function of theta and phi. Now, the math majors among us are saying, well, what if the function doesn't look like that or can't take that form? Well, we don't know at this point, right? It's perfectly reasonable that the solution to this differential equation is not as simple as two functions multiplied by each other. But I know if this works and gives me solutions, then these have to be the solutions. And that's the thing that I'm going to rely on with this, is that it's just going to, if I can get a solution, it's going to work. And if it wasn't going to give us a solution, I probably wouldn't have dedicated all this time to writing down this video. I guess I'm not writing down, to recording this video. But if I plug in this ansatz into my second order differential equation, what happens is I actually can separate that second order differential equation into two different equations, right? There's some algebra here, and if you want, you should do that. It's also in just about every quantum textbook. But if I take that and I plug it in, right, only the r gets trapped inside r derivatives. Only the y gets trapped inside angular derivatives. And therefore, there's a whole bunch of terms that only depend on angles. And those terms that depend on angles, I'm representing by this lambda here, right, which down here, right, is basically taking all of those terms that depend on angles and moving them into their own equation. Because if I'm moving in the r direction, all of those terms that depend on theta have to be a constant. And that constant that I'm going to talk about is the thing that I'm just calling lambda. And so by doing this, I've taken my problem and I've split it up into two different equations. They are coupled, right, in the sense that they both have lambda in it. They both have that constant. But one of my differential equations only exists in r, and the other one exists in the angles. And now it's important to note that the reason that I can do this, or one of the reasons that I can do this, is because the potential only depends on r, right? And so I'm not worried about parts of the potential that go into the angular part of the equation, right? So what I'm doing from now on, right, that assumption of spherical symmetry is going to dictate that the angles themselves don't have any information about the potential. And so what's left up, let me say, the radial equation is going to be the subject for the next video. Okay, that's going to be something that we're going to talk about a little bit later. For the rest of this video, I'm just going to talk about that radial equation because I can solve it without even imposing a certain or particular physics problem. What's also neat about the way that we decompose the radial equation, or how we wrote down the radial equation, is that the combination of things on the left-hand side in this equation are exactly the L squared operator, the total angular momentum operator that we talked about last week, right? That we derived the components of the angular momentum operator. If you square them and put them in spherical polar coordinates, this is the thing you get on the left-hand side, right? So there's some real physics here to this term that comes from the momentum squared, which represents the total angular momentum. And if you've taken classical mechanics, you've done this a little bit, maybe when you did planetary orbits, that you can use the angular momentum somehow as a proxy for an effective potential in the r direction. The same thing sort of applies here, but now I'm going to focus on the fact that this angular part of this eigenvalue problem is really all about angular momentum. And what also is nice about this is just by noticing that this is the L squared operator, I know what the eigenvalues are, right? Because the eigenvalues of the L squared operator are LL plus 1. And so this constant lambda, which is going to appear both in the angular equation and in the radial equation, is just going to be given by LL plus 1, and I'll talk a little bit more about that later. But even recognizing that, the task ahead of us still is to solve this equation as a differential equation, and after we solve that equation, impose the boundary conditions to see if we can come up with some quantization conditions on the things that we're talking about in this problem, right? We still really have to do steps 2 and 3, but now I only have to do steps 2 and 3 for the angular part of the equation, and I can put off the radial part of the equation until I make another video. So to solve the angular equation, we're going to go, again, back to this method of separation of variables, mostly because this kind of looks like the equation that we had before, and separation of variables worked once. Why not do it again? That's the definition of insanity, right? Anyway, okay, so if I take y, and I decompose it now as capital theta, which is only a function of theta, and capital phi, which is only a function of phi, I come up with this new differential equation. And what I want to notice here is that this second term on the left-hand side now only depends on phi, right? So in the same way that we had identified all the terms that depended on the angles and excise them, I'm now going to take the term that depends on phi and excise it, and I'm going to do that because finally, after all of this algebra, if I call that thing a constant, right, because if I'm looking in the theta direction, this thing is constant, I end up with the shoe, right? And so it took that long to finally get to a place where I can recognize the shoe, and therefore I know that these solutions of phi, capital phi, right, are going to have to be proportional to e to the, well, plus or minus, but I am phi, right? And we finally can do one of these problems analytically. I know that the phi dependence of my wave functions is always going to be in e to the im phi, right? And of course, we did this problem in one dimension before, right? And you remember all those beautiful things about the fact that because if I have a coordinate that's periodic, that tells me something about the quantization of m. We know that m is going to have to be an integer. We know all of these beautiful things that come out of that, but again, I'll tell you about that in a couple of slides, okay? But we're able to actually solve that problem. So we started with a 3-dimensional problem. We turned it into a 2-dimensional problem. We now solved one of the dimensions. And what's left, of course, is to solve the theta equation. Now, theta is a funky angle, right? Because unlike phi, which goes from 0 to 2 pi and then starts again, theta goes from 0 to pi, right? And it's not periodic, right? Because crossing 0 is not the same as crossing pi. Going across the North Pole is not the same as going across the South Pole. And so, one, I have a much more complicated equation to solve, right? I have, this is not the shoe, right? But once I solve this, I'm going to have boundary conditions that are not as easy as the boundary conditions that I have for the azimuthal angle, right? And so, what method do I use to solve it? Well, look it up in your book, okay? This is the associated Legendre equation, and therefore the solutions to this equation are a set of well-known solutions known as the associated Legendre polynomials, okay? And Mathematica knows these, your book knows these. Everybody, you can look up these in any reference, right? But what I end up with is a particular polynomial, right? In terms of what the value of L is and what the value of M is. So there's a unique polynomial for every value of M and for every value of L. And what's also interesting, right, is now we can take a look at the boundary conditions in theta, and we can learn something about what the possible values of L and the possible values of M are from this equation, okay? And again, there are lots of 2's and pi's and square roots of things and -1 to the n's. That part of writing down the analytic solution isn't so important as knowing that I have this differential equation that I can solve, and then when I impose the boundary conditions, I can quantize it, right? And somebody else has done that for us, and that's going to work for every problem where I have spherical symmetry. And so what do those boundary conditions tell us? Well, they tell us that this number L is going to be an integer that's greater than or equal to 0. Okay, so L can be 0, 1, 2, 3, all the way up. And the only solutions that exist to the associated Legendre equation are ones for which M is between -L and L. That is to say, M can be -L minus L plus 1, 0. It can be 1, 2, all the way to L, but it can't be anything bigger than the absolute, the absolute value of M can't be any bigger than what L is. Okay. And so just by looking at the differential equations and the boundary conditions, I get these conditions on what L and M can be. And that is now where we're going to promote these numbers, L and M, to the official designation of quantum numbers, right? Because they are indices that uniquely identify which angular state that I'm in, right? L has some value and then M has some value. And those two values tell me what the angular distribution of this wave function is going to look like, right? It tells me the total functional form of the angular part of the wave function. And so if I want to reconstruct the y's, right, the total angular part, well, the y's are equal to capital theta times capital phi, which is given by this thing on the right. Note, I plugged in the easy part, but I didn't plug in the hard part, right? But all of the phi dependence is given in this e to the im phi, and then all of the theta dependence is given by that associated Legendre polynomial. Okay, these YLMs, the combination of the Legendre polynomial and the e to the im phi's, are the things that we call the spherical harmonics. Okay, and this is probably a word that you heard before. The spherical harmonics are a beautiful, complete set of functions that I can always use to decompose any function on the sphere, right? So this should remind you of Fourier series, right? If I had a circle, I was able to decompose that onto sines and cosines. Those were a complete set of functions that describe the circle. The spherical harmonics are a complete set of functions that define how you can plot something on an entire sphere, which is, of course, more complicated than a circle because its symmetries are more complicated than a circle's. But it still maintains all of the beautiful pieces that I want out of basis functions of a Hilbert space, right? After all, this is still there's an operator here, right? There's a Hamiltonian that's defining what these basis functions are. And therefore, each of the basis functions are part of an eigenstate, right? And therefore, we expect them to be orthogonal to each other because the Hamiltonian is Hermitian, right? And so if I take any two spherical harmonics and I integrate them over the entire sphere together, that is, if I dot one with the other one, right, this inner product of one spherical harmonic with another, then I end up with two delta functions that tells me that this thing is either going to be zero unless they're the same spherical harmonic. And I want to come back to the thing that I say on the top of this slide here, is that these spherical harmonics are the angular part of the wave function. And so we think about that as sort of, the spatial distribution. What does this space look like in the position basis? But that also means that it corresponds to some state that's uniquely identified by those two quantum numbers, L and M, right? And so when I write down at the bottom that I can think about taking an LM and an M prime an M prime L prime and interproducting them with each other, that's really the same thing as using Griffith's rule and taking the integral of the two spherical harmonics over the entire sphere. And at the end of the day, I end up with the same thing, right? They obey the same rules because those two functions are orthogonal to each other. They're a good orthonormal basis. But what's more is that these quantum numbers mean something, right? Remember, LL plus 1 was the eigenvalue of the total angular momentum operator, right? And so L is the total angular momentum quantum number. It tells me how much total angular momentum there is, and maybe that's why it makes sense to have L equals 0, no angular momentum. L equals 1, L equals 2, L equals 3 gives us quantized amounts of total angular momentum, which is, of course, what we want to do, right? We get that from the boundary conditions. You can't just have any old angular momentum. It has to be given by h bar squared times LL plus 1. So L, right, which is this thing that sets what M can be, right, is an integer that tells me something about the total angular momentum. Well, what is M? Well, remember, M was in e to the im phi, and so when I apply the LZ operator, which is proportional to d by d phi, I get that M out as my quantum number. I get that out as my eigenvalue, and therefore h bar M is the eigenvalue of the LZ operator. Right? And so now things start to beautifully come together. L plus 1 is the total angular momentum. That's how big the angular momentum can possibly be. and LZ, or h bar m, gives me the z component of that angular momentum. And now there's a reason why in this case z turns out to be special, right? And that's because I chose my spherical polar coordinates to, have a polar have an angle theta that starts from the z-axis, right? And so when I decompose my states onto this particular set of YLM, I can only talk about the z component of the angular momentum because of the basis that I chose, right? And that's something that we're going to have to live with when we build Hamiltonians, right? Is that the shape of the, L equals 1, M equals 2 spherical harmonic really depended on what the coordinate system looked like, even though the eigenvalues are coordinate system independent. Okay, and we'll have a good chat about that later. Okay, so your take-home messages. There's an angular part of the eigenvalue equation. The solutions to that are the spherical harmonics. The spherical harmonics are physics. They tell us about the total angular momentum and the z component of the angular momentum for the quantum numbers L and M. If I want to look up what these distributions look like, I'm going to look to my book, or I'm going to look to Mathematica, or I'm going to look it up in a table or something like that. But the functions themselves are a complete set of functions that can describe any function over the sphere. But in order to get the full wave function, including the energies, right, which we haven't talked anything about. We've only talked about the angular momentum. In order to get the energies and what the full wave functions look like for any real potential, I have to take this information and I have to plug it back into the radial equation. And as I said, that's the topic of the next video. All right, see you then.